Some people used everything they knew in class, all those little tricks with we know what the normalizing constants are, and you could work through it using the gamma form and doing it's the expectation of the inverse coming from a gamma. You could write it down that way, or it's the expectation of an inverse gamma. Both will work. It's the same thing. But if you use the gamma form and you're working on the inverse, you can do the integrals kind of from scratch by knowing what the normalizing constants of gammas are, but you need to write down the normalizing constants all the way through. So a lot of people took things it'll work out if I throw them all away, and it won't. So you need to keep track of everything. So if you had gamma functions in your answer, it was because you didn't carry your gamma functions around and get them to cancel in just the right way. So some of you recognized the posterior predicted distribution had the form of a Pareto type 2. That is true. So, hey, that's cool. It is a recognizable distribution. What is it? I didn't ask you. I just wanted you to write down the kernel of the distribution if anybody wants to know what that distribution is. Some of you tried to make it look like a T because you're just tempted to do it. I didn't mark down anything for it because it doesn't matter. You still wrote down the kernel, trying to force it into a T, but keep in mind this thing is always positive. So it's not a T. Nobody said it was, I don't think. So I've seen that before. It's a Pareto. So if you want to know, like, okay, you got another distribution, Pareto type 2s are the posterior predictive for a Bayesian analysis using the conjugate prior. That's cool. If you ever study reliability theory, they pop up there too. So some of you looked up the answer to the expectation of the variance for a Pareto type 2. And just as long as you recognize the parameters, okay, I think that was all right. I wouldn't mind seeing some work involved in there, but I don't think I was heavy-handed on that at all. But if you treated everything like it was a gamma and you didn't get the math right, I probably marked off a few points there. So there were a number of ways to do that problem. You didn't actually need to recognize the distribution to work through it, but if you did recognize things as either you needed to know properties of inverse gammas or Pareto type 2s and you looked them up in tables, that was fine. So, because I said it was open book. So lots of ways to carve through those problems, and probably a good exercise for yourself, and this is what I did all through grad school. If I could think of 3 different ways to do the problem, I would do it. And sit down for an hour doing it 3 different ways. I wouldn't turn it into anybody except show my neighbor, hey, check this out, they all work. I go, yeah, of course they're supposed to. But really it's just practice, right? You get used to doing it. If you want to do that and show me the 3 different ways, if you can figure out a 4th way to do it as well, I'll give you 5% midterm credit. So there's some points for you. So if you do want to go through it and add all the different ways you can think of doing problems, I'll give you a few percentage points for that. I don't have any rigid rules on here because I don't think the grade is the most important thing. I think understanding the material and getting the opportunity to show that is the important thing. So let's keep everything in stride in that spirit. We will do a review session on Thursday, so you can ask me any questions about the midterm then. Happy to answer. We can also talk about the homework that's coming up and it's due. Homework 4, the next one is going to have you implement a lot of the things that you're writing down. So the full conditionals from the RAP problem. It's not a difficult problem as long as you can write down the likelihood and factorize it correctly. So lots of chunks in the full conditional end up becoming constants depending on what you look at. It's going to be all conjugate analysis, so all your distributions are going to be like gammas and normals, and there is a Wishart distribution that appears. And I'll tell you about that on Wednesday. Okay, let's get into it. Let me tell you about the RAP problem. This problem appears in the Gelfand and Smith series of papers. In one of those papers, I posted to the webpage. I kind of like it because it's kind of butchered. So it's so old-fashioned. It's like typewriter done. That's how it used to work, you know? You don't know how lucky you have it, I guess. So now you just need to know more stuff, so it's a double-edged sword versus your typewriter. But it's kind of humorous. We can talk about the analysis. I want you to see if you can recover their answers. And if you do, I'll be impressed. So, and I'm going to ask you in the next homework, how much do the priors matter? Because they pick some values in those priors, the hyperparameters, where it's like, where'd that come from? And that should be the thing you go back and run off and look at, because I asked you to read the paper already. If you ever want to know anything, ask a question, ask about the hyperparameterization. What difference does it make? And you'll notice that they probably do make a difference. So this is not my favorite analysis in the world, but let's take it with a grain of salt. It was like 1989. It's a long time ago. Anybody born before 1989? Is that all of you guys? None of you guys? Sean? No, not even close, right? Am I the only one that was born before 89? No way. Wow, it's happened. So, cool. Graduated high school in 1993. Go Raiders.
You're not gonna like the answer when I was born.
You know, I guess it's arbitrary, right? You want to tell us, Sean?
It's 2002.
Wow. So, Sean's a baby. He told me Sean is an undergrad. Sean told me that I wasn't going to like him. I was going to be trouble for him all semester. And Sean did exceedingly well on the midterm. So no problems whatsoever.
Paperwork that
no problems. No problem. So good job. So keep up the rate of ascension and you're going to do great. Okay. 1974, if you must know. So December 5th, it's coming up, so I will expect a party. Okay. Today, threat model. This comes from Gelfand and Smith. This is one of my favorite papers when people tell me about the 1990 version. The 1990 version that appears in JASA is one of the most cited papers in Bayesian land. So people will often go running and cite that paper when they implement a Gibbs sampler or something like that. Put that in your literature review and nobody will argue with you. So it's probably one of the correct citations to put in there. Probably not the paper that I gave you. So it's more like a tech report. There's 3 of those. So like that, where they're kind of just working through Gibbs sampling. My guess is Gelfand and Smith weren't interested in the analysis so much, but we will talk about the analysis. I think it's important. I don't think they got it wrong. I think sometimes you can be rather clumsy and still get reasonable answers. So I'll tell you what their major question is, but I think from their perspective, they were looking for an opportunity to highlight a Gibbs sampler. So let's not pick on too much about the model because nowadays we can compute models they couldn't compute back then. So we have a little bit of sympathy for them. They're both stars. They know what they're doing. They would probably agree with us. Okay, so here's the model. So I'm going to say, what was did I use W's or did I use X's in the homework? Y's? Okay, well, I'm just going to make up my notation. So it might be a little bit different. I'm going to call them W's. I, T. So this is going to be slightly varied notation from what's written down in the homework. So hopefully they're close enough that you can recognize everything. This is going to be the weight of rat I at time t. Those are my indices. So the idea is they've got a batch of rats and they're tracking their weights through time. So they're going to give the rats some treatment. In the data set, how many rats do they have and how many time points do they have? How many rats? It's low. You guys didn't write the paper. 6. So that might be the number of time points. So it's actually not data rich. It's just a few rats with not too many time points.
There were 5.
Yeah, I think there were. So look at that. Saying that there's a number of parameters in the model, and let's keep in mind that these parameters are associated with each other. So we're not just getting 5 IID samples, we're getting 5 samples that are dependent through time. So there's going to be a lot of dependencies in the model. And so if everything was independent, an IID model, we wouldn't be able to estimate everything. But because there's associations between everything, we'll be able to do our estimation. So idea is they are going to inoculate the mice with some treatment, and they're going to see if it puts on weight or takes off weight. So let me just ask a question, just so we can put this into the scope of our own minds. Do you think that the weight that the rat initially came into the study with is going to determine how fast it puts on weight or takes off weight? Let me ask the question a little bit differently. If you go to the gym and you see somebody that's just starting out at the gym, will their size walking in have something to do with how fast they put on weight or take off weight? Question is it faster or slower? So if they come in big, does that mean they're going to drop weight faster or put on weight faster? And I guess it kind of depends. So I could argue it both ways. That somebody that comes in, it depends on what their weight is attributed to. But I could imagine if you come in and you have weight to shed, you could shed it quicker. But also, if you come in and you're trying to build a bunch of muscle or something like that, maybe a big person is able to put on weight faster. So I can imagine that their initial weight has something to do with how fast they put on weight throughout the study.
It's like initial proportional too, like if you're already big, then adding 1 pound is, or losing 1 pound is much less than the smaller.
Yeah, I would kind of think that too. There's a relative sort of thing. So you see it on, I can't remember what the name of this show is. I don't want to get too into details here. But it's like, yeah, there is a rate of, 10 pounds, losing 10 pounds is hard to do. So it actually shouldn't be that hard. But I'm not giving up ice cream. So, but somebody else that was maybe 600 pounds, taking off 10 pounds might be easy to do. So, or putting on weight, if they were all of a sudden trying to put on weight, maybe they can put it on faster too. So, and we've seen this at the gym. So, same question about the rats. So, they're going to do some treatment to them, and they're going to watch whether or not they put on weight or take it off and see how it's related to each other. So let's just think about this right here. This is the model we're going to write down. I'm going to say every rat in the study, that's the I index, that's the rat right there, has its own parameters for putting on weight. All the rats are different. So this is like a statistical model. Not like, it is a statistical model. We're not really thinking about the genetics involved or any of that. We're measuring trends, and we kind of have these proxy parameters where we're not modeling the biology or the physics of the parameter, but we're just kind of looking at trends. And we're going to interpret those trends maybe as a proxy for the real science. So here's their time series model. I didn't come up with this. We could argue about this. It's probably not what I would write down these days, but we have a lot more computational facilities than they have in the past. So rat I is going to have an intercept and a slope. And here's how we're going to model time. I'm going to model this. I think I used J in the homework, so I'm going to make this T. This is actually the T index. It's the exact same T that's right there. So this is a linear model. And I'm going to add some air. Air IT. So you might imagine this is normally distributed, centered at 0, and it's got some variability to it. And I'm going to write it down like this. V is equal to 1 over sigma squared. So you can interpret that parameter however you'd like. If you interpret it as phi, the conjugate prior is gamma. If you like dealing with sigma squared, the conjugate prior is inverse gamma. And so the midterm kind of had you think through that. You're going to do the same thing with the Wishart once we get there. think about it two different ways. So is this reasonable? I would probably ask, is the variability the same for all the rats? Do they really vary the same? That doesn't sound very plausible to me. But maybe it's close enough that this is a reasonable model. And we'll assume maybe they check stuff like that. But this is the model that they use in the paper. So they do deal with things on alternative scales. So the paper deals with that. And you're going to deal with that. And one of your exercises is to interpret how to go back and forth between the two things. So if they use some inverse gamma, and you use a gamma, then you need to be able to encode it back and forth. So it's basically an exercise of looking at tables and how do you transform between those two different distributions. So it's a transformation exercise. They use inverse chi-squareds just to make it even more fun. So for you, but remember that chi-squareds are types of gammas. So the inverse chi-squared relates to the gamma. And that's not a unconventional thing to do if you're British. So if you're American, you probably do that these days. And the old Brits probably thought about that and applied inverse chi-squared priors to them. And they're equivalent in some sense. You know, through transformation, they're conveying the same amount of information. So Adrian Smith was the senior most author. That's why he probably went last, you know, in the 1990 paper to give his junior colleague, you know, a little bit of extra credit, is the way I see it. They're both superstars. So this is the model. So what we're thinking about is at time 0, this part disappears, and this is like the initial weight. That's at least kind of how I interpret it, but I'm not just locking it down to be the initial weight. So in something, let me just say why you wouldn't want to do that. So think about babies' weights through time. They grow through time. They get bigger and bigger. So if I were trying to model what a baby's weight looks like, I might see data that looks like this. I'm going to draw this just a little bit different. Maybe I see something like this through time, and this is weight. And so I probably wouldn't say, well, I know at time 0 when the baby doesn't exist, it weighs 0. Because it doesn't really work that way. And so it could very well be, so I probably wouldn't lock that in to be the intercept, because then I'd probably do something like that, where the right thing to do would be maybe to draw that line. And so this is the whole conversation about extrapolating outside of spaces, that this might be highly nonlinear in that part of the space. So you don't want to describe that as linear and impose what the intercept is. So rough rule of thumb is always estimate the intercept. Now interpretation is a little bit interesting, that if maybe that came out to be negative or something, I wouldn't exactly interpret it that way. But this is a proxy for the initial weight of the rat. It has something to do with it. So let's kind of think about it that way, but let's remember we should estimate that and not just plug that in as the rat's weight at the initial time, because we're trying to fit all of this data the best we can. And by locking that thing down, we might not get an optimal fit. So always estimate your intercepts. Please do that. If you don't, probably all your interpretations of everything are off. If you're interpreting things like R squared, I assure you your interpretation is off if you don't estimate the intercept.
So are you saying instead of essentially choosing a value for alpha,
We're going to estimate it.
right, you're using the fit?
Yeah. Yes.
Even if that value doesn't make logical sense?
We'll figure out a way to think about it.
Right.
So we'll figure out what logical sense means later. So yeah, we're gonna estimate this. So we'll estimate. And what I'm saying is, it's more logical to do this, regardless, and get the fit right, you know? So if we're going to interpret and forecast and predict out of things, that's probably the most important thing. If you really wanted to impose something, you might say it's got to be positive. So, and if you didn't want to do that, you might want to go to a nonlinear model to really fix things up. These are the things that they're avoiding. This is the propensity to put on weight. Or taking off. So if that was positive, you'd be putting on weight through time. And we could definitely interpret it that way. And that's probably what we're really interested in. Or if it's negative, you're taking off weight through time. I'm not saying that this is a great time series model. This is probably the silliest time series model I've ever seen, but this smacks of what they used to do during the 80s. They had to do the math, and I think they really wanted to bring up this question of, are these two parameters related to each other? So now I'm going to interpret these right here. So these rats have these parameters. They were given to them through their genetics. So here's the way I think about it. This is probably what happens in reality. There's a large bucket of alpha I's and beta I's out there for every rat. And when each rat is born, a rat angel comes down into the bucket and pulls out those parameters and attributes them to the rat and says, these are your parameters for life. So, and they're coming from some distribution. So they're grabbing these parameters out of this distribution. So those are random parameters that are assigned to the rat. And this is about what I was told when I was a child. So it's how the world worked, but it wasn't quite that statistical. I don't think this is what happens, but this is maybe what we're thinking about, is there's a lottery pick for your genetic parameters. And so we're going to model those. And I'm going to say the alpha I, beta I come from some distribution. This is the distribution that they chose, probably because everything works out really great. Everything is conjugate in some sense. And you can do all the calculations and write down a Gibbs sampler. So there's going to be some initial centering parameters. So these are going to be the center of our random effect distribution. So random effect distribution is you've got some groups that are more associated than other groups, and you want to model that. So what are the groups that are more related than other groups? It's the rats with themselves through time. They're more related to themselves, and so we want to model that. So they let this be a dense matrix. This is just a 2 by 2. So this will have the sigma squared for alpha. This will be the sigma squared for the beta, and then I've got my alpha beta term, my covariance term in here. So that's going to be my covariance term that's going to model it. So this thing right here, I'll just call it squared. We could have called it sigma. Maybe we should have done that. You can put in a 1, 1 and say that's associated with this thing. And the 2, 2 term is associated with that. And the cross term, the off-diagonal term, is what's associating those two parameters together. So this brings us back to the original question of what's that? So this is what they want to know. Are they related to each other, and if so, how? So what is that covariance term? What is the correlation between the two things? So we might ask, is it negative? Is it positive? So how does their initial weight relate to the propensity of the rat putting on weight? So they want to know all this stuff. Now we could quibble about this model, and if we were going to have fun, we would do this for a couple hours. So and try to design a better model. We're going to stick with it and just accept it as this is what they did. And know we could do better, but the idea is they're going to march through a Gibbs sampling to try to learn all these parameters. So here are the full conditionals that you would need to work through. And I'll say the name of the game to identify the full conditionals is to write out the likelihood function for this whole process. So keep in mind, I goes from 1 to n, and then t goes from 1 to cap t. And I might have called this j or something like that. I probably used n for the I. So you write out that likelihood. Just keep in mind, for each rat, you sample these parameters once from everything. And so you're reaching into this distribution once, boom, getting its parameters, and then you're rolling that thing n times to get the time series. So every time you do a stochastic calculation and you think about what's going on, that term should appear in the likelihood. So how many times will this term appear in the likelihood function? N. So each rat has one of those. They sampled their rat parameters once upon appearing. I don't know, whatever we want to call it, existing. So then how many times does this thing pop up? Right here. We have to roll that t times. It keeps coming up over and over and over again. Think about how you would sample the data out of this model. For each rat, I would grab one of those, then I would roll this thing t times. How would I write down the likelihood for that? I'd product them all together. All those little stochastic steps. So there's a normal here, joint normal for each rat, and then I roll this t times for each rat. So I've got these t normals multiplied by 1. Now I need to product that whole thing up n times. So I'll let you think about that. We can do that in review. We maybe write down some more details next time as well. So what we need to do, the name of the game, is to write down our priors. So our priors that we're going to use for, I'll say, phi, we'll use a gamma. That would be the conjugate choice. You'll have to pick these things, so I'll call it alpha phi, beta phi. The paper has values that they picked, but they put it on an inverse chi-squared scale and they modeled the variances. So you'll see if you can encode those. So we also have to have priors on the alpha 0, beta 0. I'm just going to call that theta 0 just to make everything nice. My recommendation is to come up with some nice matrix notation to make your life very simple. If you're working in sums of squares, I guarantee you're going to make lots of mistakes. You won't recognize your answers either. But the answers you'll get out of this stuff will smack of what you've seen on the homework and in the midterm. They'll just be standard distributions that you'll get for all your full conditionals. We'll let this be a normal. You'll have to pick some parameters here. So this thing right here is the big question. This is going to be inverse Wishart. And I need to introduce you to this distribution. Instead of working with sigma, I could work with sigma inverse. And this will be Wishart. So next time I'm going to show you that the Wishart is the conjugate prior for the precision matrix, and I'll show you how to work through that calculation. And then I think on the homework I asked you to work through it in the other way, where you're working through it on the other scale. So you're modeling sigma itself. And so just so you know, when you're looking at everything, you'll probably need to run to an inverse Wishart table to answer questions about sigma. And I'll tell you what all the parameterization is in terms of sigma inverse. But if you're getting this stuff, you'll be able to seamlessly move between. Seamlessly meaning you pull out a table, look at it for 15 minutes, do the pattern matching and go, okay, I get it. That's what I mean by seamless. If it takes a half hour the first time, that's not a big deal. So this is what we're going to study. So let me just tell you real quickly what the likelihood looks like involving this term right here. So this stuff just looks like this. This is going to be sigma inverse e to the minus 1/2. I'll call this theta I, just to give us some matrix notation. This is going to be theta I minus theta naught. Transpose. So this is a vector that looks like in that direction. Sigma inverse theta I minus theta naught. Make it like that. So you might be asking, what does this look like in terms of this parameter right here? And the answer is it's Wishart distributed. And I'm going to come in next time and I'm going to show you what a Wishart distribution is. If you are familiar with what a Wishart distribution is, you'll say this isn't written right. There's a trace up in the top. And I'll tell you how you get the trace. You just drop it straight in there. Does anybody know why I can do that? It's a scalar. So keep in mind the thing upstairs is a scalar and the trace of a scalar is a scalar. So the exponent is this. Now I can do some rearrangements with the trace. And I'll tell you some properties of traces next time. You can cyclically permute all of these things and put it into the form of a Wishart. So next time we'll kick it off with this model. I'll write down some more details about this model so that we can see all the stuff we need to update. For the homework, all you're doing is writing down the full conditionals. I'm not asking you to implement, but later on you'll implement this. So make sure you understand it really well. Let me give you back your exams, and then we'll pick up with this on Wednesday.